lab, you will do an extraction from Nutmeg, followed by a Spartan assignment. Please make sure you read your handout before coming to lab and be prepared with your notebook complete.
Of the lab. First of all, this lab is going to be using materials from the introductory organic lab, so 2251. Any of these procedures that you don't remember, it is very important that you go back and review those methods, as those methods will be required for you to understand what you're doing in this lab. This pre-lab lecture, as with all of your pre-lab lectures, have embedded questions that you must answer to get credit. It is not based on just watching the video, it's based on watching the video and answering these questions. The questions are going to be based on your pre-lab reading and this video. It is very important that the first step is to read your pre-lab through perusal, engage with that. So start that as soon as you can so that you can then move on to the pre-lab lecture. Remember, the pre-lab lecture is before you start doing anything with the lab. But you must read before that pre-lab lecture. So pay attention to the video because all the answers are either in the video or they're in your pre-lab reading. You only have one shot at answering these questions, so make it count. Week number 1, as I said before, is the extraction of trimestrin and the purification of that trimestrin from nutmeg. Step number 2 is the hydrolysis of the trimestrin to myristic acid. Myristic acid is formed first by the hydrolysis of the trimestrin to the carboxylate. So the myristic acid doesn't initially form. You actually make the carboxylate ion, and then the carboxylate ion gets protonated by an acid to give you the myristic acid, and then the esterification of that myristic acid to give you the methyl ester. So overview, you've learned in 2251 about lots of extraction methods. So overall, what you're going to be doing for a lot of the labs this semester is that you're going to be extracting natural products. And examples of extraction of natural products are getting sugar, sucrose from sugarcane, getting penicillin out of the Penicillium fungi. That was a natural product extraction done in a chemistry lab. And also cocaine from coca leaves and cocoa butter out of cacao and things like that. So your first part of the lab is that you will be extracting some compounds out of nutmeg, just like how people extract coffee from the coffee beans to drink. So the coffee that you drink, what they do is use hot water to remove that because it's a faster process. You're going to get it the coffee out faster, and the coffee will come with caffeine. So if you wanted to extract caffeine, this is actually how you do this. So caffeine powder comes from coffee or certain types of tea. It's insoluble in water, but by heating it up, it becomes more soluble in water. You get it out crude, and then you do some purification. So you'll do some two types of recrystallization. One you learned in organic 1, and one is kind of a different version of that. And then you'll get your material.
So for your extraction, you're going to be setting up your extraction very similar to how you did your reflux reaction in organic 1 at the end. You're going to use your micro scale distillation setup. You're going to make sure it's not the one that's a fractional with the little metal. So it's going to be your small scale from your micro scale kit. You're going to have your diethyl ether in your flask. Commonly, dichloromethane is what's used. One of the things chemists will sometimes do implement green chemistry is to look at what are common substitutes for dichloromethane. Ethyl acetate is a potential one. So if you were to try to do this experiment, let's say again, you could try ethyl acetate to see if that would work. There are some published studies with diethyl ether, so that's why you're using diethyl ether. But if we wanted to do like a project and see if the ethyl acetate worked, this could be an example. You could try acetone, but I know the acetone doesn't work as well. It dissolves too well. Some of the material and tetrahydrofuran. There is a version of that, a methyl tetrahydrofuran, that's greener. Tetrahydrofuran itself is actually not green. And so we choose the solvents because we want to dissolve the trimethystin, but we don't want to dissolve some of the other stuff. And that's why we're going to stick with the diethyl ether. It's safer than the dichloromethane, which is suspected to be a carcinogen. And what you'll do is you'll put your flask in your sand bath, but be very careful. You want it to be a low enough temperature to boil, but not to boil over. Diethyl ether boils at a very low temperature, so you just need this warm. You don't need it hot, so don't crank it up too fast. You just need to get it to the boiling point of your mixture. So once you get this heating in your sand bath and you get the temperature to get to the boiling, make sure you have just one of those micro scale caps. You put the little septa in it, that little round plastic piece. Don't throw them away. They're a little expensive. And then your little metal cap. So it's this metal cap, it's kind of open in this area. And then you put the septa and just stick it on the top. Don't screw it in. You just want it to help with the vapors not coming off, but you don't want to tighten it or you're going to create too much pressure and that could be dangerous. When you do your setup, you're going to put your hoses so that water goes in the bottom to rise into your condenser and flow out into the sink. So make sure that your setup is near the sink in the hood, as close as you can get, because it's going to be a little bit challenging otherwise. Make sure that your hot plate is on a jack and already screwed up a little bit so that if the temperature gets too hot, you can just lower the jack and so you can quickly lower the temperature. There's no other way of lowering the temperature. So in the previous page of your slides, I'd mentioned that dichloromethane is potentially harmful.
All right, so in your extract.
So using that information that dichloromethane is a potential carcinogen, there's some green solvents that you could choose out of to try to see if this reaction could also work. What was the solvent that was just mentioned? So in your extraction, you are going to be taking your filtrate from your bottom flask after it cools down, and you're going to be filtering it through a pipette that has some cotton in there. So you're going to take a plastic pipette and you're going to pipette out the liquid as best as you can and filter that out, because there is other things that are also in that extract. So not just the trimethystin, but all the solid particles, some carbohydrates, some other things that are in there that we don't want. So we're going to run it through a pasture pipette that has cotton in it, or it might have steel wool or like a wool-like material that's in there, and that will get rid of all the extra particles. But it's not, your sample is still not pure. There will be a few things in your sample that are not going to be easy to remove just from filtering, because they're also dissolved. So as such, what you're going to need to do is filter, get your material, and then you're going to evaporate off the solvent. So you're going to evaporate off the diethyl ether, which should be fairly fast. And you're going to be using that to do a recrystallization. And we call this a crude recrystallization because you're going to have to do this a second time. But we're going to do a crude recrystallization so that next week we will do our next experiment, which is going to be to hydrolyze that trimerisin. So we're going to break down that trimerisin from the that fat that it is into fatty acids, and we're going to evaluate that. So you're going to get this crude material in your notebook. You're going to find your IR and GC data, any of your spectral data. You're going to find that directly in your notebook. But the first week you're really going to extract, evaporate solvent, and then recrystallize. And so for our next video, we'll talk about a small amount.
Adding a small amount of solvent to dissolve everything. So our first one is just adding a set amount of the acetone to remove the initial impurities. And then the second one is the true recrystallization. And that true recrystallization, like you started to talk about, you put your sample, so you have your sample in a of your solvent. So let's say this is acetone. You get it to boil, right? So you may have a boiling stone in there. And then you take your crude trimestrin, actually it should just be like some little crystals on there. Let's just pretend these are your solid. So you should have some crystals. And then you're just going to pipe it a little of your hot solvent. So you're going to put a little bit of hot acetone until there's a little bit of liquid, not a lot, but because the acetone needs to remain hot, how are we going to do that? So now we take the little bit of crystals with a little bit of acetone. Okay, it shouldn't be dissolved. It might be, a couple of pipette drops of it, just enough that there's a little bit of liquid sitting on the bottom. You should see liquid sitting on the bottom. And then you're going to place this on the hot plate, right? And you're going to put that on there to keep it warm. So keeping the acetone warm, the pure acetone warm, we're just going to keep adding until all crystals are gone or dissolved. But only to the point that it just dissolves. You want this solution super saturated. So if you have too much solvent, it will completely dissolve and then nothing will recrystallize back out. So once you're done, you take this and you put it on a cooling mat and you don't touch it. So you have your liquid, and eventually you should start seeing slowly crystals form at the bottom. Okay, so this is a true recrystallization. So basically what you're doing is you're adding as much hot liquid as possible to get it just to the point that it's fully dissolved, but not any more than that. So we want it super saturated. You're going to let it cool and leave it alone. So this might take 15 minutes-ish, maybe 20, as long as you start seeing crystals form. Now, if you don't start seeing crystals form, let your professor know. They may have to have some techniques to help your crystals form, or you may have too much solvent. So then you put it in an ice bath to cool for maybe another 5 to 10 minutes. Okay. Number one is don't stir, don't shake, Don't swirl. Don't even stare at it too hard. Leave it alone while it's cooling. Leave it alone while you have it sitting on the counter. Leave it alone in the ice bath. It needs to cool slowly on its own. If you stir it up, the impurities will get back into the crystals and you'll have an impure sample. Now, when we say recrystallization, sometimes the compound that we recover at the end that we want is the crystals as our pure substance. Sometimes the impurities are the crystals and it's the liquid that we want. In the case of our lab today, it is the crystals that we want. So one of the two things, either the liquid needs to be pure or the solid needs to be pure. It's usually the solid, but not always. In this case, it is the solid. So to recrystallize, you need to add enough hot solvent too. And then when it is cooled, what do you need to do? What's going to happen? Now, remember, like I said, this is not specific to this lab for this question. This is in general. The second part of the question, pay attention, look at what's in general going to happen. Not necessarily just this lab. In general, what is going to happen?